I'm going to introduce the procedure known as integration, and I'm going to show you an interesting property of integration. All right? So, integration is the process, or integration is a process to calculate the areas underneath the graphs of functions. All right? Integration involves finding the limit of approximations involving rectangles as the number of rectangles increases without bound. Okay, so let's step back and make sure that we're all on the same page. Integration is a process to calculate areas. Okay, that much is certain. What areas? The areas under the graphs of functions. Okay? What is this procedure to calculate areas? We're going to approximate the areas with lots of rectangles, and then we're going to increase the number of rectangles to improve the accuracy of our area approximation. And then if we take the limit of, as the number of rectangles increases without bound, we'll get an exact value for the area. All right? Now, let me say that last part in a little bit differently in case anybody was confused. All right, so approximating an area with several rectangles, hopefully that's not too difficult to accept, and hopefully increasing the number of rectangles to improve the approximation is not too difficult to accept. Now, taking this so-called limit as the number of rectangles increases without bound, well, that may or may not be easy. All right? So we will talk more about that in future videos. But for right now, just know that mathematicians have defined a very special limit to almost seemingly do the impossible, which is figure out the exact area calculation you would have if you had an infinite number of rectangles. Okay? Now that's a lot of words, so maybe I should do a picture now to maybe make it a little bit more concrete. All right, so suppose we wanted to calculate the area underneath f of x, and let's say f of x was equal to the expression x squared. So you may know that the graph of x squared is a parabola. All right, and let's say we were interested in the area between the x values, x equal to 0 and x equal to 2. Okay? So we're interested in the area underneath the red curve and above the x-axis between the origin and the purple vertical line segment. Okay? And so we can get an approximation with a few carefully selected rectangles, and we can add more rectangles to improve our approximation and keep adjusting the widths and heights carefully. Okay, so that's where we're at. Now, And so somehow we would have to take the limit as the number of rectangles increases. Okay? We have notation for just such a procedure to calculate the area. Okay? So what we would do is first we write an expression that looks like we're asking for the antiderivative of the function. Okay? However, to denote the fact that we're interested in the area, not the antiderivative, we're going to put the left x value, the x value of the left side below the antiderivative symbol, and we're going to put the rightmost x value above the antiderivative symbol. Okay? So when we put numbers like that, then this is referred to as a definite integral. And now we're interested in calculating an area, not calculating an antiderivative. Okay? So for this specific function, of course, we would replace the f of x with x squared, and it would look like that. Okay? Now, if you wanted the area, let's say, between x equal to 10 and x equal to 20, that would be denoted by the integral in the bottom right. Okay? Now, that is all I'm going to say about integration for right now. And if you're concerned or worried or curious about this limit and how you're going to figure out the limit as the number of rectangles increases without bound, hold that thought. Okay? Right now, I want to go back to something that I said in a previous video. In a previous video, I discussed the relation between antiderivatives and areas. All right? Suppose that I wanted to calculate the areas of my 4 rectangles using antiderivatives. Let's assume that the rectangles all have the same width. So they all have a width of a half. Okay? And let's also calculate the antiderivative of x squared. All right, I'll call it, let's call it capital A for antiderivative. And the antiderivative of x squared is x cubed over 3. Actually, let me be careful with my language. This is an antiderivative because we know that there are an infinite number of antiderivatives. Okay? You can use any valid antiderivative, and what I'm about to say is going to hold for all of the antiderivatives, but I'm intentionally choosing the simplest one, okay, for clarity. All right, so what I said in a previous video was you can find the area of rectangle 1 by finding a specific difference in antiderivatives. So you could, for that one, you would evaluate the antiderivative at 1/2. That's the x value of the rightmost point on the rectangle, and then you would subtract the antiderivative evaluated at the leftmost x value. So apparently that difference in the antiderivative gives you the area of the rectangle 1. Okay? And likewise, you can calculate the area of rectangle 2 by finding the difference in the antiderivatives. Okay? And I can calculate the area of rectangle 3 by finding the difference in specific antiderivative values. And as I said before, this seemed kind of overkill and unnecessary perhaps, since we already know how to calculate the area of rectangles, but just bear with me. All right, so I have there 4 differences. Each of those differences represents the area of one of my 4 rectangles. If I sum all of those differences together, I get the total area of, or the sum of all the areas of the rectangles, right? Okay, watch this. What is the sum of all those differences? Well, notice something interesting. We have some cancellation. We have the function evaluated at 1/2, and then we also are subtracting that same value, aren't we? And then we are evaluating the function at x equal to 1, and we're subtracting that value as well. And we're evaluating the function at a equal 3/2, and we're subtracting that. All right? So apparently, everything goes away, and the sum of all our areas apparently is equal to what? I'll write it below my area that I'm interested in. It's a of 2 minus a of 0. That was the only thing left after all the carnage, right? So I can calculate the sum of the areas of those 4 rectangles by finding that difference. Okay, now pause the video and think about how that red expression would change if I had 8 rectangles instead of 4. And if I had 80 rectangles instead of 4, or 1,000 rectangles. Okay? Think about that for a second. Okay, now I will continue. So as you add more rectangles, you will have more differences to add up, right? Just like I have on the bottom left side. But you'll also have more calculations. No matter how many rectangles you get, you will get the situation where the only thing that survives is a difference that involves the x values of the right side and the left side. Notice that 2 is the x value of the right side of the area in question, and 0 is the x value of the left side of the area in question. Okay? So apparently, if I wanted to calculate an area approximation that had 1,000,000 rectangles, all I have to do is use that red difference and save myself the trouble. If I wanted to calculate an area approximation that involved 1,000,000,000 rectangles, still the same difference. Hey, what about all this limit business? Can I just take this limit instead? Absolutely. Okay. Now I'm not going to say that's always going to work. There's some exceptions. There's some functions for which this trick does not work, but for many functions it does. Okay. So what does this all mean? So the area underneath this parabola, x squared, with respect to the x values between 0 and 2, apparently we can just calculate the following difference. A of 2, that's 2 cubed over 3. A of 0, that's 0 cubed over 3. So apparently the whole mess simplifies to 8/3. Look at that. Okay? 8/3 is the area. All right? Now, make sure you understand what I just did. Okay? Pause the video if you have to. Okay? I'm calculating the area under a graph. In other words, I'm doing the process of integration by using a shortcut trick involving antiderivatives. Now you're seeing why I was saying that this was this amazing discovery. All right? Okay, let's now do an example to hopefully increase your confidence in this procedure. I'm going to calculate an area by this procedure that you already know. That's why I'm hoping it'll increase your confidence. All right, so suppose that I had the graph of a function, And suppose that let's call the function g of x to make it different from the last function name. And let's suppose that g of x was linear. So let's suppose that g of x, let's say, looks like this. Okay? And let's label the endpoints and make it clear what we're talking about. So let's say that it has a y-intercept of 2. Let's say that the purple vertical line segment is at x equal to 4. All right. And let's say that the top is at x equal to, we'll make it 4. All right, so what is the area underneath that graph? Well, we don't need integration for that. You might be able to see that you can approximate the area, you can interpret the area as a triangle and a rectangle, right? So the area is the area of this triangle and the area of the rectangle added together. Okay, so let's do it that way, and then we'll see if the integration procedure gives the same answer. Okay, so this top point is 4, 4, and then the other side is 0, 2. All right, so the rectangle has a horizontal leg of length 4, a vertical length of length 2. The rectangle has a vertical side length 2. The area of the rectangle is base times height, which is 8. The area of the rectangle is 1/2 base times height, so 4. And so the total area is 8 plus 4, which is 12. Okay, now let's use integration and see if we get 12 as well. All right, we're going to have to figure out the function g of x. So g of x is equal to mx plus b for some m and b. The b is 2 because that's the y-intercept, so mx plus 2. The slope is 1/2. So 1/2 x plus 2. Let's evaluate g of 0 and g of 4. G of 0 gives 2. Yep, that checks out. G of 4 gives 4. Yep, that checks out. All right. Now let's calculate the integral of g of x from 0 to 4. So that's the integral from 0 to 4 of 1/2 x plus 2. All right, and what we're going to try to do is use that antiderivative trick. So what is the antiderivative of 1/2 x plus 2? All right, that is, well, I'll call it a of x again. So a of x, where a is the antiderivative, is x squared over 4 plus 2x. All right, and so we're going to calculate a evaluated at 4 minus a evaluated at 0. A evaluated at 0 is 0, so we can ignore that. A evaluated at 4 is 4 squared over 4, that's 4, plus 2 times 4 is 8, and that gives 12. Lo and behold, we got the same answer. Okay? Now, you're not going to be able to confirm that integration is giving the same answer for more complicated area calculations. All right? However, I can make the following comment in closing. All right? if the function is piecewise continuous. All right, so you can divide it up into pieces such that each piece is continuous. Okay, then it's possible to prove that the integration procedure will give the correct value for the area. All right?